So suppose a function is defined parametrically. Y is defined in terms of x, but not directly. Y is defined in terms of t and x is also defined in terms of t. So this is very common. For example, in the equation of circle, equation of ellipse, parabola, hyperbola, we have parametrically defined functions. So when we want to find derivative of y with respect to x, then that will be derivative of y with respect to t and derivative of x with respect to t. This is how we find derivatives of parametric equations. So let us do this. Differentiate. All right, I will write better is find dy by dx. This is type 3. First case was the general rules of differentiation. Second was implicit functions. Third was parametric, type 3. Find dy by dx for the following parametrically defined functions. Parametrically defined functions. So the first one, x is equal to e power minus t square and y is tan inverse of 2t plus 1. So find dy by dx. So I'll do one problem. Later you can do some others. So dy upon dx, when we want to find, it will be dy upon dt by dx upon dt. So now dy upon dt upon dt. So it is d by dt of tan inverse of 2t plus 1, which is 1 upon 1 plus this argument square into derivative of 2t is 2. So that's what we get here. We can simplify this. This is 2 by 1 plus 4t square plus 4t plus 1. So dividing by 2, you will get 1 by 1 plus 2t plus 2t square. Now what is dx upon dt? d by dt e power minus t square. So the derivative of this is e power minus t square into minus derivative of t square, that is 2t. Therefore dy by dx is dy upon dt by dx upon dt. So dy upon dt is this. And divided by dx upon dt is e power minus t square into minus 2t. So dy by dx will be, on simplified note, it will be minus for sure, e power t square upon 2t into 2t square plus 2t plus 1. So this is the answer. This is a parametrically defined function. So we'll do further types. So second, x is a times of theta minus sine theta, and y is a into 1 minus cos theta. Find the dy by dx. Find dy by dx, not dy by d theta. Easy question. So dy by dx will be dy upon d theta by dx upon d theta. So derivative of y with respect to theta and derivative of x with respect to theta. So now dy by d theta is like this. This is y into a into 1 minus cos theta. Now dy by d theta will be a into derivative of 1 is 0 and derivative of cos theta is minus sine theta. So minus of minus sine theta will be plus sine theta. Okay. Now next, x is, now x is a into theta minus sine theta. So dx by d theta will be a into derivative of theta with respect to theta 1, derivative of sine theta with respect to theta is cos theta. Therefore dy upon dx is dy upon d theta, that is a sine theta, by a into 1 minus cos theta. So we can simplify this, a cancels, and then the sine theta can be written as 2 sine theta by 2 cos theta by 2, and this 1 minus cos theta will be 2 sine square theta upon 2. So we can cancel this off, and one sine term also gets cancelled. You are left with cos theta by 2 by sine theta by 2. So you will get cot of theta by 2. Okay, this is the second. Now I'll give you another one. All right, this type sometimes you get and get. Sometimes, rarely, you don't get a lot, but you get, like, differentiate cos inverse 3 cos x minus 2 sin x by under root 13 with respect to sine inverse 5 sin x plus 4 cos x by root 41. Okay, look at the solution here. Now let u be cos inverse 3 cos x minus 2 sin x by root 13. Okay. Now I'll deal and let v be sin inverse of 5 sin x plus 4 cos x by root 41. We need to find du upon dv, derivative of u with respect to v. So consider u. Now we'll simplify u. Consider u as cos inverse of, say this, 3 cos x minus 2 sin x by root 13. I will write this as 3 upon root 13 cos x minus 2 upon root 13 sin x. Now I'll write let cos alpha be 3 upon root 13. Therefore, sin alpha will be 2 upon root 13. So 9 plus 4, 13 you will get. Okay. So now you square and add, you will get 1. Square and add, you will get 1. So we can write like this. Therefore, u is cos inverse of cos alpha cos x minus sin alpha sin x. So what do we get? This is cos inverse of cos of alpha plus x. Cos a cos b minus sin a sin b. It will be cos of a plus b. So therefore, cos inverse of cos of course depends on the value. Assume that these are within the primary domain. That means x plus alpha plus x lies between minus pi by 2 and pi by 2. Assuming this, you will get u as alpha plus x. Not minus pi by 2 to pi by 2. It is actually 0 to pi. I'm sorry, for cos inverse cos. Assuming this lies between 0 and pi, you get this. So u is alpha plus x. Now let us consider v. This is 1. Consider v. Now v is given by sin inverse of 5 by root 41 sin x plus 4 by root 41 cos x. So let see sin a cos b plus cos a sin b. So let cos beta be 5 by root 41. Then sin beta will be 4 by root 41. because when you square and add 25 plus 16, you get 41. So if this is cos, this will be sine. So therefore, V will be sine inverse of cos beta sine x plus sine beta cos x. So this is sine inverse of sine x plus beta. So assuming that x plus beta lies between minus pi by 2 to pi by 2, the principal domain. So you get this is x plus beta. V is x plus beta. So this is 2. So u we got as x plus alpha. V we got as x plus beta. So this implies du by dx is equal to 1, and this implies dv by dx is equal to 1. Therefore, du upon dv is du by dx by dv by dx, which is 1 upon 1, which is equal to 1. All right. So this is the way we solve. Here, just the concept of inverse trigonometric functions. That property we have to use.